All right, so in this section, we're going to continue marching on. We're going to look at some more models. We're, in this case, actually going to expand on something we've already talked a little bit about before, and it's this population dynamics. But I don't know if we probably won't spend any class time on them, but there are other types of equations that you'll see that turn out to be nonlinear, but you still have techniques to solve. But the homework in this section is almost all population dynamics with a couple of extra other models, but they give you the formulas, they give you the differential equations, and when you have to solve them, as long as they're separable, you can use the separable technique to solve a nonlinear model. Where things get hairy and where we're not really going to spend much time right now is if the nonlinear model isn't separable or exact, then we don't have a technique to solve it, and we'll talk about how to handle those a little bit later on in the semester. I originally had on the schedule for us to cover 3.3 next time. I've decided to skip it and dive straight into higher order. I want to get moving a little bit faster through a couple of things than I had originally planned to, and then I'll come back to systems later on. Systems are just differential equations where you got multiple variables. One of the funnest systems that I did in my research was taking the model that you guys already know how to do, the mixing model, right, where you have something coming in, something going out, and you have an assumption that the inside of that tank is thoroughly mixed. Okay? A system might have two tanks connected to each other, or three tanks connected to each other. Something's coming into one tank, that tank is feeding into another tank, that tank is feeding into another tank. Maybe that third tank feeds back into the first tank, but there's also an outlet valve on some of these. It's a closed system in that, well, actually, it doesn't have to be a closed system. You have stuff coming in, stuff going out of the whole system, but they can all be interacting with each other. That's kind of a fun model to solve, but where we put that into application was on, I think I may have talked about this in linear algebra. There was a government contract that I was working on where my job was to build a real-time simulation of a contaminant release inside of a building where we thought of every room as a separate tank, and we thought of the doors and even the walls as separate ways of exchanging airflow from one room to the other, and there were also connections throughout the building with the HVAC system. And so the question became, if somebody released a contaminant in one room in a system like a building connected by HVAC, how does that contaminant disperse throughout the building? What's the contamination over time? Which is basically a concentration mixing problem with a whole bunch of tanks. That's all it was. And so we were able to solve those in real time. Now, where things really get messy is if you don't assume the tanks are thoroughly mixed, right? If the contaminant is, like plumes of gas through the room, that is computational fluid dynamics, which cannot be done in real time, not even with numerical approximation techniques, not accurately. So we ran those models, but they took like 3 days to finish the simulation. Then we could visualize what happened inside that room. But if you're trying to build a gaming platform, which we were building a gaming platform for training for the Army, for their combatants, that they would go in and move through this building on a Call of Duty style kind of game. Instead of having their weapons out on the game, they had the little meter that I built for them that had a dial that showed the concentration level of the different contaminations within each room. But all it was solving systems. So we're going to solve systems, but we're going to push that a little bit later on. But the nice thing, again, about those mixing problems is they're nice and separable, and even the systems are easy to solve. Let's talk more about the applications. In this particular section, the nonlinear models I want to talk about here, I want to take our population modeling to the next level. We started with the simplest of all possible models. Remember what we called the Malthusian, actually it's an L in there, Malthusian model, which named after the mathematician, or actually I don't even know anything about him, but the guy's name is Malthus. He assumed that population growth was proportional to population. So you got dP dt is equal to kp. You recognize that. We solved it in the last section. Nice linear model. But what we're going to do now is we're going to kick this up a notch. And we can think of advancing the Malthusian model a couple of different ways. It turns out to be equivalent whether we think about it algebraically or whether we think about it with respect to the physical model. But here's the idea. If I were to divide the p to the other side, I got dp dt. That is, this is the rate of change of p divided by the population is constant. Okay? I'm not broadcasting to you, am I? 5, 4,
it's loading.
2, 1, broadcast. There we go. So, really what I'm talking about here is let's think of this ratio. Rate of change to the population. The Malthusian model says that ratio is constant. So as the population increases, that means the rate of change of the population has to also increase to maintain that constant. So what if the ratio between the rate and the population is not constant? Maybe it depends on other time-independent mechanisms. Not changing over time, but that it has something else to do with p. In fact, that's easily written as dp dt divided by the population is some function of p. And what that function of p is will vary based on what kind of model we want to assume. But again, we want this to only depend on p because we want to consider this as an autonomous system that doesn't really matter where we started. It would evolve similarly over time. Now, the logistic equation is basically assuming f is the next level complicated function. So if it's not constant, let's take it up one level and call it linear. So that's one way to approach this. I want to think about this with respect to the model. When we assume that the population's growth is proportional to the actual population, the resulting curve was this exponential, right? It grew without bound forever. So as it started out slow and then bends upward and eventually has that curve. Now you know that in real life, in the real world, there would not ever be any such growth that can grow unbounded forever. At some point, your population has to level off in a physical reality because of, for one, carrying capacity. Like if you're in a petri dish with bacteria, it can't grow exponentially because it'll run out of room to grow. The human population on the earth will run out of space, right? Any animal population, same thing, okay? So we're going to assume that the population has something called a carrying capacity. So here's the idea. When you're nowhere near the carrying capacity, when your population is nowhere near n, you will have a Malthusian model. That is, it's proportional to your population. But as you get close to n, then your rate of growth should slow down. Right? You should slow down as you get closer to your carrying capacity. The further away you are, you should grow faster. Okay? But at the same time, the larger your population is, you should grow faster. What I'm basically summarizing there is that the rate of growth is now jointly proportional. It's proportional to both the population, so as the population increases, it grows faster, but also it's proportional to how close you are to the carrying capacity, which we can measure as n minus p. Right? As p gets close to n, that gets small, which means your population rate should go down. But as p is far away from n, that's large, so your population would be growing faster. But if it's jointly proportional to both of those, what that means is that dp dt is, and I'm going to use that little proportional symbol that I introduced to you earlier, it's proportional to the product of those two. So, your differential equation, as an equation, not as a proportionality statement, is equal to some constant times p times n minus p. Okay? That's one way to think of what's called the logistic equation. I'll call that equation 1. Or, equivalently, we can think of it not in terms of the model, but back here in terms of this ratio. If dp dt divided by p is some linear function, a, and I'm going to just use the standard one that is usually in these texts. It would be like mx plus b, right? In this case, a constant times p plus a constant a. To make it look like what is usually done in the analysis, and there's reason for this later on, I'm going to write it like this. That's a nice basic little linear thing. So you could also write dp dt as p times a minus b p. That is essentially an equivalent form with a different set of parameters. The logistic equation number 2. Notice, by the way, these are the same thing if A is Kn and B is K. Or N is A. Well, actually, I should write it this way. Sorry about that. Or, let's erase this. K is whatever B is. So say you're given the equation number 2, you could rewrite it as equation number 1. Just let K be B, and then N is A divided by K. Right, they're connected to the same equation with just different parameters involved. So if you knew it, if you were written, you're given the equation in A minus B P form, you could figure out the carrying capacity as just letting K be B, and then N is A divided by K, or essentially A divided by B. Okay. Now you've seen this one right here before. Right? We actually did a phase portrait of him in the example where we were learning how to do qualitative analysis. And that's really all we did with it, but we'll come back and see that picture again. So the general logistic equation, what I'm going to work with throughout the rest of this chapter is P times A minus BP. That's the general one. Okay? That's all I'm putting in that blank. You don't have to write it again if you already have it. You can just draw, say, an arrow, but that's that blank. Okay. So, what we haven't done yet, but we can do quickly, is solve that equation. Well, relatively quickly. Should be careful with my language there. First of all autonomous differential equations, and let me pause there. Do you know what autonomous means? Do you remember what autonomous means?
Relies on only one.
Yes, which variable though? Dependent variable. Right? Because the one on the right-hand side, like on this one, is P. Right? P depends on time. It doesn't depend only on time. It's, in fact, time independent. The differential equation is time independent. So that's what this means to be called autonomous. By the way, all autonomous equations are then, by definition, separable, because all you got to do is divide all of those to the left-hand side and move the dt to the right-hand side. No t's on right-hand side. That's what autonomous means. So the equation is separable, which means solving should be a piece of cake. So that's what you get when you divide this across to the other side and move the dt over to the other side. You get this. You want me to try to integrate that on the left? And don't say Wolfram alpha, please. It's like my favorite, well, third favorite, integration technique. That's not even an integration technique. Reverse of chain rule is integration by parts. Just so. Actually, the reverse of the chain rule is essentially substitution. It's use substitution. The reverse of the product rule is integration by parts. But either one of those help us here. There's a better one. For the record, I hate trig substitution. It's the worst. It's the devil. If I ever have to do it, I quit. Actually, I just had to teach it in Cal too. And I told everybody I hated it, so I'm sure they're all going to learn it with great passion. How do you solve something like that? Nope.
Isn't it just natural log of that?
Oh no, because you got the product, p times a. So before I fill in the blanks, just as a review, do you know how you integrate something like this? There's a couple ways. Actually, the way that I'm thinking of is, first of all, to do this. 6 divided by factor. X plus 4, x minus 2. So you take the 6 over the x plus 4, x minus 2, and you set it equal to You've seen it before. It's got a name. And the worst. Oh, it's the best. Oh, it's a fun one.
No, I remember this.
And then you equalize.
It's long. It's actually fairly tedious in most cases. But anytime you can introduce a technique in mathematics that handles a whole group of functions, always, and it always works, I like it. So I like this one because I can now integrate all rational functions with this technique. It's called
Partial factor?
partial fractions.
Oh, that's the one.
Oh, baby. Okay, so I've got this integral here. I've got to finish it before I come back and do the actual problem we're working on. So the way that my trick for doing this is, first of all, multiply through by x plus 4, x minus 2, times the whole thing, right? You get 6 equals a times x minus 2 plus b times x plus 4. And the calculus textbook tells you to multiply this all out and set the coefficients on the left equal to the coefficients on the right. But that's dumb. That takes too long. What you do is you just pick a couple of good x's to find your a's and b's. What would be a good choice for an x? This has to be true for all x's, so I can pick an x and make it true.
0.
0's not good, but 2's good. Why is 0 not good? I got 0, I have an a and a b still in there. But if I put a 2 in there, then the a's are gone. Uh-huh. And then what's the other good choice? Yep, x equal 2 means that 6 is, that's gone. I shouldn't mark on that. That means that's gone. I get b times 6, right? So b is 1. Then you get x equal negative 4.
So you get 6 equals a times a negative 6, right? Which means a is negative 1. So what I actually have now is the integral of a, negative 1 over x plus 4, plus b, which is 1 over x minus 2 dx. And those are both easy to integrate. Negative log of x plus 4 plus log of x minus 2 plus c, or log of x minus 2 over x plus 4 plus c. Y'all know what I did there, right? You know your properties of logs?
What happened with negative?
The negative is like up here as to the minus 1. It's what puts it in the denominator. It's like subtracting two logs. If you take a log of a minus log of b, it's log of a over b. This is like log of x minus 2 minus log of x plus 4. So it's log of x minus 2 over x plus 4. With the plus c out there. But either one of these is right. This is right. This is right. But the trick was, if I can split a complicated, that is a product, a quadratic in the denominator, into the sum of two fractions that have linear in the denominator. Linear is easy to integrate because it's just logs. I heard is so...
That negative that you put up so high, is that for the ln as well? Or for the natural log? So,
It's a negative out front.
yeah.
Right, it's like a constant.
On top.
So I move it up into the power. So it's like log of x plus 4 raised to the minus 1.
So the entire
But you
part
can
is
do,
the
but you
minus
didn't
one.
because you.
No, just the inside.
Just the inside.
Yes. Yeah. It's the property that says log of, well, I should do this.
Okay.
M log of a is log of a to the m.
Okay.
And you could also just think of it as log of a minus log of b. That's log of a over b. Either one of those. That's how I'm writing this. Okay. So that's how I handle when I have quadratics or polynomials in the denominator, right? I split it. So let's come back up and do this one. All right, so I've got on the left-hand side 1 over p times a minus bp. So I'm going to write it as a over the first factor plus b over a minus bp. That is the second factor. Okay, so what do I do first? Multiply by the denominator on the left-hand side. So p, a minus b, p. And I get 1 equals a times a minus bp, because the p's cancel, right, when I multiply this times each of these, plus bp. So I got to find capital A and capital B. How do I do that?
Set P to 0.
That is now a very good choice. P equals 0. 1 equals A times little a. That BP here is 0. This capital B, capital P over here is 0. So you get that your A is 1 over A. If you let, what's another good choice?
1.
Yeah, you can do anything now because you've got this one over here. Actually, I'm going to be even sneakier and do
If I do A over B, well, why? Why would I choose A over B?
Because you're cheating.
What does it do?
Cancel out the A and B.
Makes this 0,
Right.
right? So I'm thinking in my mind, what's something that makes A minus BP 0? Well, it's got a B in the denominator, so I can cancel out that B. Put an A in the numerator, A minus that. Gone. That's my reasoning. Just thinking critically here. That gives me 1 equals 0 plus B times A over B. So capital B is B over A. Okay, so now my integral of 1 over P A minus BP dP is the same thing as the integral of, so I'm looking at this right-hand side of this now. Instead of A up top, I have a 1 over A. Just sticking this here. A equals 1 over A up here. So 1 over A divided by P, or you could pull it out front.
You can just put that, can you put the A down there?
Yep. What do y'all like? Do you like this? Do you like this?
I like that one.
Is it preference?
Shouldn't matter. I mean, it's gonna. We're gonna have to simplify it anyways. But you got, that's what the A. This one becomes plus. You got B over A times A minus B P. I just want to make sure everybody sees where I got those. All right, so I'm gonna, just for simplification, I'm gonna split this into 2 integrals. Just add it together, dP, dP. The first one I'll factor out the 1 over A, so I just have 1 over P inside. The second one I'll factor out the B over A, so I'll just have 1 over A minus BP on bottom. Okay, so what's that equal to? Integral of 1 over P dP. So I have 1 over A times the log of P. I could put absolute value around this, but considering that I'm talking about population dynamics, should be positive, so I'm going to be lazy and not put them on there. I mean, the reason it's good to put them on there is that you might expand this model to be talking about other things besides population, where logistics still plays some role. But in this context, population, positive, I'm going to do that. Plus B over A. All right, so what's the integral of this guy? I would do U equals A minus BP. So du is a
That doesn't work.
negative B dP.
Oh, yeah, it does.
So actually, I'm going to take this guy. I'm going to stick him back inside there. I'm going to put a minus there and a minus there. So now I've got my minus B is my du. There's my u here. And out front, I've got just a minus 1 over A. That's just integration magic. And then you've got the integral of 1 over u, so it becomes natural log of u, which is A minus B P.
Why did the negative one next to B, why did it become negative?
Because I needed a negative inside because of this. So I multiplied one in and divided one out. Or I multiplied one in, multiplied one. And those two minuses together is the same as the plus. So I just changed that plus to a minus minus. And then this minus inside becomes part of my du.
that minus outside has to carry through.
Not become these, oh, you have that, right.
Now, if you check this, if you took the derivative of that right there, you do get this. Right? 1 over a minus bp times the derivative of what's inside is a minus b. So that minus b times the 1 over a out front gives you that b over a. It works. Now, keep in mind, all of this was
The integral, or equal to the integral dt.
right. So now, we're going to set equal to the left, nope, yeah, the right-hand side. Right-hand side of 1. So equals integral t dt, which is just t plus c. So I have this equals this. And if I did that correct, that's what's at the top of the next page. Jackpot.
But how is it the integral of t dt?
There's not supposed
There's not a t there. It should be integral of dt. Hold on, I'm stretching. Oh, now I'm erasing. If I go back up, so here's the magic of OneNote for you. I can do this. This is this. You don't have to draw all of your notes to do that, but that's where I got it, okay? And then Control Z. That's gone. Sweet. Okay, now let's solve that for P. Can you do that? Can you solve for P?
Sure, why not?
What do you think? How would we get P by itself in this mess of messiness?
Let's probably by a first.
Okay, so I have natural log of P minus the natural log of A minus BP equals AT plus C. I'll call him C1. Okay, now what? Let's do something about the two different logs first.
Oh, let's divide them.
Yes. Log of P over A minus BP equals AT plus C1. Now,
Oh, this is C1.
well, when I multiplied the A, technically it's AC, right? So, it's a new C. I don't want to keep track of all the mess that goes on the arbitrary constant. C1 is that guy. Now you do the E thing. There's a verb for that. Exponentiate both sides.
Yes.
Exponentiate.
E over
Eify it. P divided by A minus BP equals
e to the at.
E to the AT times E to the C1, which is maybe, I don't know, C2 out here.
Yes, of course.
C2 is really just E to the C1. It doesn't matter because we're going to find the C that we want when we do the initial condition in whatever final form we have the equation. That is, I could plug in initial conditions up here and find that C and then solve it, and then whatever number ends up here is the correct number. Or I can keep modifying my C to be an arbitrary constant and then solve for that C whenever I get to the end.
Can you show me? Can you do the exponentiation of the right side real quick?
So E to the AT plus C1 is E to the AT times E to the C1. right? When you have a to the m times b to the, or sorry, times
Right,
a to the n, you get a to the m plus n. You
Okay.
can just go the other way.
Yeah, I'm good.
There.
Thanks.
Thought bubble. All right, still trying to get p by itself.
Multiply by. Oh no.
Yeah.
Multiply by p and then.
No. Multiply by something.
A plus BB. Wait, no, that's not it.
Here's my thought. If I could move this over here, if I took just this guy and move him over, right? Then I distribute, I'll have a term that has a p in it. Move that back to the other side that also has a p in it by subtracting it, and then factor out the p. Right? So let's multiply both sides. A minus BP. That gives me a p on the left, and then a C2. I'm just going to drop the 2. I'm tired of keeping track of it. A constant times A times e to the AT. Well, let me do it in steps. I don't want to do it all at once. C e to the AT times A minus BP. And distribute this to each of those.
Right.
So you have CA e to the AT minus CB P e to the AT.
Oh, and add.
And then add the CB P e to the AT back over here. So I have, and then factor out the P on the left. P times 1 plus CB P. Nope, the P's gone. E to the AT. And on the right, this is gone. All you have is CA E to the AT. And I still wrote that P in there like I'm an idiot. Come on.
You're right, right. It says B. It says
C beat.
Yeah.
So P now is CA e to the AT divided by 1 plus CBE to the AT. Which is good, but it could be even simpler if all I did was replace, actually, if I multiplied the top and bottom by e to the minus AT. The only thing that's not so simple about this, although it's perfectly fine, is I've got 2 of the same factor, e to the AT on top and on bottom. If I were to multiply by e to the minus AT on top and e to the minus AT on bottom, I actually only have that exponential showing up once in the whole expression. Because on top you have CA. On bottom, if you distribute this to both of these, you have e to the minus AT plus CB. Which is exactly what I had written right there. Whew. Sometimes I worry as far as we go that I'm going to end up in a different spot than I was.
We'll make it a thing where once a week we'll invite like an intermediate algebra student and just watch their brain melt.
That's why I would leave all of my notes on the board whenever we were done in like linear algebra. Try to melt the Cal 3 brains last semester.
Except for that didn't.
That's
really
true,
work.
because the ones that were in there were already
Those just said already been vector mechanics. They're like,
been there, done that.
that was a little. Yeah, just it's like the same.
Okay, so there's your P, but here's the thing. I mean, it's still got the constant in there, right? And if we go back to the original problem, I don't think I actually even wrote it all the way out, but if I scroll back up, this original problem of dp dt, right, this general logistic equation that we just solved, that's your differential equation. But let's now assume that we know the initial value problem. So I'm going to give that to you now and say, let's consider the initial condition of P of 0 is equal to P naught. So instead of having an arbitrary constant C in there, we're going to have this with a P naught in there so that we can just plug in what the initial population is into the solution. I know you're going to hate me for this, but everything we just did, you don't have to do again, because this is the logistic equation, right? We're going to use whatever we got out of this. We're going to use this every time in our homework even. So all of this is now so that you have the honor of knowing where it came from, that it was not bestowed on high from some oracle. It is actually something that makes sense, and you have a proof for where it comes from. All of that being said, let's find now what C is when we plug in P naught. So everywhere there's a 0, no, everywhere there's a T, put a 0, set it equal to P naught. So that means P naught is AC divided by BC plus 1.
Oh, right.
And what's our unknown? What's the thing we are solving for?
C.
Because A and B are parameters in the original equation. We already know those. P naught is the initial population. We already know that. So now, solve for P naught. What do you do first? Trying to get C by itself.
Or multiply your BC plus 1 and then distribute and then subtract.
Okay. Yes? Other way around.
No. C equals P over
P naught. Yeah, I had it upside down. You had it right on your paper, I'm certain. But I had it wrong. That's correct. Nice and simple little C. So we plug him back into here.
No.
PT equals little a times P naught divided by A minus B P naught divided by, this is why people love applied mathematics, by the way. It's never neat. It's always messy. You just keep going until you get it as neat as you can. But it's still the right answer. It solves a real problem. It's because the real world is messy, that's why. And then you have a B times P naught over A minus B P naught plus E to the minus AT. So how would you simplify that?
Do the same thing again. The multiplication, distribution,
Yeah, it's actually what I did with the E thing, right? I just multiplied the top and bottom to cancel out the denominator. In this case, I'm going to multiply by a minus b p naught. I mean, that's the trick we teach in even college algebra. When you see a complex fraction, you can get rid of all the internal fractions by multiplying through by the common denominator. So in this case, that's just multiply through by a minus b p naught on top and a minus b p naught on bottom. And the good news is you get that right there. Right, because on top that cancels. When you distribute this to each term, the first one it cancels. The second one you'll just have a minus b p naught e to the minus at. Okay, so here's the big things you really need to know. I hope to have refreshed your memory about this technique, which will come back again. But it was just a link in the chain, a tool that we needed to be able to answer the question. We were able to solve this logistic equation using our separable technique and a little bit of algebra, cleaning up the mess, and then find the initial conditions, impact on the C, and now we have a final formula that depends on whatever the A, the B are given. Again, notice, if you happen to know something like up here, the carrying capacity, if you knew N and you knew K, you could find the A and the B, or if you know the A and the B, you can find the N and the K. Okay, we're going to answer a few more questions about these in just a second, but I'm going to scroll down here and ask you, what we typically always ask once we get a solution is, what happens in the long term? What is the long-term behavior of this solution? So, take this guy right here, and we're at a p naught divided by b p naught plus a minus b p naught e to the minus at. Let's take the limit as t goes to infinity. There's no t on top. The only t on bottom is right here. So what happens to e to the minus at, assuming a is positive, by the way, as t goes to infinity? 0? Infinity. So you get e to a minus a times something that's getting very, very big.
Approaching 0.
The numerator is now getting large but negative, which is like 1 over e to the something very large, right? So this goes to infinity, but 1 over infinity goes to 0.
But because we're 1 over again,
Well, just this piece goes to 0. Notice there's this thing over here that's not being affected by that e.
isn't that one constant?
It's constant. So what you have is a constant over a constant plus something going to 0.
So 1.
So it gives you that, right? A p naught over b p naught, but the p naughts cancel. It actually goes to a constant. It goes to the constant a over b. So the solution of this thing approaches a over b. Does that surprise you?
No. I'm less surprised and more just like,
Sure, whatever. I'm delirious by now. This is 2.1 in your notes. This is this problem right here from 2.1. See it? dp dt equals p times a minus bp. You've seen it before. What did we do with it? We found its phase portrait. And then we drew pictures of what the curves look like. Now, we've assumed all the way through here that the population is positive, so don't worry about what's happening down here. But what's happening up here as time goes by?
It always approaches the population.
And what is this right here?
A over B.
It was the critical point for that differential equation. That is, it was what made the right-hand side 0. It was A over B, right? That middle point in your phase portrait was A over B. So we've now verified that this solution that we've come up with is consistent with the phase portrait that we created before. Right? In fact, if we gave any P naught would be where we started on the y-axis or on the vertical axis, we should see that the equation that we came up with are these curves, depending on where we started. Okay. The other thing I wanted to point out here real quick is that if you started with the model form of that logistic equation, remember this is the same thing as P times, just if I distribute the K, it's Kn minus Kp. So there's my A, there's my B. So A is Kn. And what was capital N? What did it represent in the model? Carrying capacity. It was the maximum population that the surrounding medium that it was living in is supposedly able to handle. And B is K, so what's A over B? Makes sense, right? That your population should approach its carrying capacity and won't be able to pass it. If you start below it, it will approach up to it. But if you start above it, your population will die off and approach it from the top. If you have more than you can handle, right, then they starve or they don't have what they need to survive. That's reflected in the model. I'm just going to draw real quick for you the picture that I already showed you when I went back from 2.1. This was A over B. This was 0. It was down up here, up in between here, and down here, which means all my curves look like this in between. Which is generally what is thought of as the shape of a logistics curve. Oh. Okay. So that was all kind of preparatory to be able to answer the types of questions you need to answer in this section, which are, let's actually do some problems that use those models. Good news is, if it's logistics, you don't have to resolve. But if I make a slight modification to this, you may have to repeat some of these techniques. Okay. Suppose a student carrying a flu virus returns to an isolated college campus of 1,000 students. If it is assumed that the rate at which the virus spreads is proportional not only to the number of infected students, but also of the number of students not infected, determine the number of infected students after 6 days. If it is further observed that after 4 days, 50 people are infected. All right, build what they tell us here. First of all, to build the differential equation, what's the key information that's been given to you? Well, we don't really have a population. Well, I guess we kind of do. We have a carrying capacity of 1,000. So that's like your N. Okay. Really, it's this phrase right here that captures the essence of the logistic. That it is proportional to the number X and the number not infected. okay, which would, by the way, be 100 or 1,000 minus x, or n minus x. So your dx dt, the rate at which the virus spreads, is proportional to x and 1,000 minus x. So here's what I'm going to do to work this problem. I'm going to move the k inside so that it is in my standard logistic form. Independent variable times, this time it's 1,000 k minus kx. There's your dx dt. Again, I'm comparing that to dp dt was p times a minus bp. And by the way, what's my x at 0? How many students are infected? Yeah, exactly, Matt. 1. 1 student returns infected. So 1 in my entire population is infected. We're going to model how many are infected over time. So instead of having to solve this, we now take advantage of the fact that this is exactly that equation. Right? And we know the solution to that one. The solution is A I have to look at P naught over B P naught. Is it plus? Plus A minus B P naught e to the minus AT. Okay, so in my problem, all my x's are now p's, or all my p's are now x's. What is, what's A?
$1,000.
1,000k. It's got both, yeah, it's the whole constant there. We don't know what k is yet. We're going to actually end up using this right here to find k. B is k. The number times your dependent variable. And of course our initial condition x naught is 1. Or p naught, whatever you want to call it. So x of t, I can now write the solution down immediately because it's a logistics model. On top I have a p naught, so 1,000 k times 1 divided by k times 1 plus 1,000 k minus k times 1 e to the minus 1,000 k times t. Now let's just simplify that a little bit. I have 1,000 k on top. I have k plus 999k e to the minus 1,000 k t. Oh, and I can do this, right? So I actually just have 1,000 divided by 1 plus 999 e to the minus 1,000 k t. And I'm running out of space. But that's my x of t, but I still don't have enough to be able to answer the question, so I'm going to use this to solve for k. So x of 4 equals 50. So how do I use that?
50 equals 1,000 over 1 plus 999 e to the k4.
Negative 1,000 k times 4, yeah.
Yeah.
Is that okay? I took this extra information they gave me. Are y'all with me? I know a few of you are following me. Is everybody with me to this point? All I did was plug in what I knew into the logistic model and got this simplified a little bit. And now I'm using this next observation point, the at x value at time 4. After 4 days, 50 students have been infected by this flu virus. So I set it equal to 50 and plug in 4, which gives me a negative 4,000 k. So solve that for k. Dot, dot, dot. I'm running short on time, so I'm going to...
K equals 9.9057 times 10 to the negative 4.
Right, and then when we plug it back in and multiply it by 1,000, I think I get that a negative 1,000 k turns out to be negative 0.9906. So I'm going to stick this right here into my model. Right, oh, where am I going? Right there. So this right here is what's right there.
So you don't necessarily have to solve for k.
Right. I mean, I solve all the way for k and then plug it back in. I've got to multiply by a negative 1,000 anyways. So if I solve for that negative 1,000. Yeah. So now I've got x of t. My actual equation is 1,000 divided by 1 plus 999 e to the negative 0.9906 t. And the question we are asked is what happens on day 6? How many are infected by day 6? Now that's just a calculator problem. I think I get 276 students. When I plug that in.
Yeah, 276.
Okay. All right, I got 7 minutes to tackle this next one. Any questions about that one? Oh, baby. Okay, the next problem, I'm not really going to work it all the way. In fact, I'll kind of give you some tips of what you would do to finish this problem, but it's the same question, except that to find the parameters, you're given a different set of information. No, actually, that's not even true. It's the same type of problem where you plug in your A and your B, but where things get messy is, well, now I've got to go ahead and work it. You're given your initial condition, right? There's your N naught. The other piece of information that you're given about this, you've got community of people being exposed to a particular advertisement. We're claiming it's governed by the traditional logistic equation. Okay? Now up here on the problem we just did, it was another logistic problem, but you were given enough information to find all the parameters. The first thing you were given, of course, is the initial value. The second thing you were given is the capacity, the 1,000. Right? And the third thing that you were given is another observation. Well, that same amount of information is given down here in a slightly different form, in that they're telling you that the limiting number of people who will see the advertisement is 50,000, and they give you another condition. Okay? So here's how I would do this, how I would get started. I would start with dn dt is equal to, and I would do it the same way we did the previous one. Write it as k in times, and now I got to use a different variable because my carrying capacity is in my previous problem. Give me another variable that I'm going to use for carrying capacity. No, because we don't have a C in our final form of the other one. So C for carrying capacity. Man, I can't write today. Minus N. Only now, what is C? I don't even know why I needed the variable. I could just put the 50,000 in there, right? Because the limiting value is the carrying capacity. And then repeat what we just did. Dot, dot, dot. The point of this exercise, or me explaining this, is for you to realize that in different contexts, that idea of a carrying capacity can reflect something differently in the model. In this case, because we're measuring how much exposure they have, the limiting amount is that carrying capacity. It's what it approaches in the model. Okay? I'll let you write the answer down so that you have it, but you could check your work if you wanted to try this again yourself. You get 351.65 divided by 0.007033 plus 0.6963 e to the negative 0.7033 t. Okay. Again, in this case, A would be 50,000 K, B would be negative K, and your P naught is your 500 from up here. All right, last thing. They may throw a couple of curveballs at you in the homework. It changes the way that your final answer shows up. But you can kind of see from the model equation how you would do this. Imagine if your population happened to be the number of fish that you're stocking in a stock pool. So you're running a fish farm. People come and they fish at your place, right? And you stock it occasionally, okay? Well, the population of your fish, if you weren't stocking at all, might be governed by a logistic equation because your pond is only so big, it can only hold so many fish, it can only support so many fish, so there's a carrying capacity, okay? So in your stock pool, over time, you would reach that capacity. Well, let's say you, instead of adding fish, they'll procreate and do their thing, and you've got plenty of fish all the time, except now you're harvesting them. Either folks are coming in fishing, or you're taking out a group and you're sending them off to be processed. But you take out a certain amount every unit of time. So the harvesting equation right here basically becomes take your logistics model of what would happen if you weren't harvesting at all, and then subtract however much of that population you are removing for each unit of time.
Would your,
So just minus h.
would it be H of T?
Well, if it's a constant, like if you are only taking out 30 fish per month or 100 fish per month, you just put that 100, whatever your unit of time is here, put in that constant rate that you're taking out. Now, h could be a function of time if it varied based on time, but the simplest model would be assume that you're harvesting at a constant rate, on average.
Right.
Your average constant rate. If you're restocking, it would just be a plus. This could also be used to model a population with immigration or immigration, right? Immigration meaning folks coming in or leaving, immigration folks coming in, right? If you know those rates. Another mathematician by the name of Benjamin Gompertz proposed a variation of the logistics equation so that instead of a minus bp, we consider a minus b log of p, which turns out to be a useful equation in, as I mentioned here, actual populations, but also growths of tumors and even some other actuarial predictions. The difference comes into play whenever you start to solve this and you split this thing by partial fractions, how you actually integrate that left-hand side whenever you have a log in there. You're not asked to do that integration in your homework, but you may be asked to work with this a little bit. You'll see the questions as you get in there. That's all I have on 3.2, and like I said, I'm going to skip over 3.3, and we're going to dive into higher order systems starting on Tuesday.
10:41 on the 18th of February.
I took one more. I think I owe you like 6 minutes now.
I don't think anyone cares.
Hey, you paid good